Now, let's talk about the Bayes rule. The Bayes rule allows to calculate conditional probabilities from uh, from the data that we have. We already talked about Bayes rule very briefly when we talked about NBA example. You remember our example that probability that you will play in NBA, given that you work hard, is very close to zero. On the other hand, probability that you work hard, given that you are an NBA player, is close to 1. And the Bayes rule essentially allows us to update our knowledge about certain facts given the information. Now, let's consider a specific example. Bayes rule applied in medical diagnostics. We have a patient, Alice. She's 40 years old, and she got diagnosed with cancer. She got a positive mammogram. And we would like to answer this question. What is the probability that she has cancer given that she has a positive mammogram? Now, here's what we know about mammograms. We know that mammograms are 80% accurate, meaning that the detection rate is accurate in 80%, meaning that if you do have mammogram, it will in fact detect it. And also, it has 10% false positive rates, meaning that if you do not have cancer, in 10% of the cases, mammogram will be positive. So let's write down this in terms of the probability. So 80% detection rate means that probability that the test is uh, positive, the mammogram is positive, given that you do have cancer, is 80%. And also we know that we have 10% false positive rates, meaning that you do have a positive mammogram, given that you do not have cancer in 10% of the cases. So this is the specifications of the testing procedure, and that's something that company that develops this test will identify. Usually it comes from the historical data. And we also know that the prevailing rate of breast cancer among people like Alice is 1%. So the prior probability that Alice has cancer is 1%. So that's what we know, and what we would like to calculate is the probability of the cancer given that she has positive mammogram from the quantities that are given to us. Now, surprisingly, a lot of the doctors, when they are asked what is the probability that Alice has a cancer, given that she has positive mammogram, would give you 80%, based on the fact the test has 80% detection rate. So this is a common mistake to confuse probability of tests being positive given cancer and probability of having cancer given that the test is positive. So the fact that this one is 0.8% doesn't mean that this number is 0.8%. So this is false. And a lot of doctors get it wrong, unfortunately. All right. So let's look at this graphically. Here is an example where we have a population of 1,000 women. So each little square here is 10 people. We have 100 squares. And out of those 1,000 people, we have 990, which is 99.9%, that do not have cancer. And another 1%, and 1% out of 1,000 is just 10 women. They, in fact, do have cancer. Okay, so 1 square out of this whole matrix are the people who have cancer. Now, among those people who actually have breast cancer, 2 of them will be missed because you remember test is 80% accurate, meaning that it will miss 20% of the people. So in 2 of the cases will not be labeled correctly as people who have cancer. And 8 other cases will be correctly labeled by the test as people who have cancer. On the other hand, out of this 99.9%, which is 990 healthy women, 100 of them will be labeled as people who have cancer because the cancer has 10% false positive rate. And 890 people will be correctly identified as healthy people. Now, so let's look at this. We will have, if we test all of those 1,000 women, we will have 8 women who were correctly identified, and then we're going to have 100 women who were incorrectly identified. So we're going to have 108 people who were labeled as people who have cancer or people who have positive mammogram. Now, out of those 108, actually only 8 people truly have cancer. So the ratio is quite low, meaning that the fact that you got, if you get tested positive, if you have positive mammogram, you're one of those 108 people, and only 8 of those 108 people will actually have cancer. Okay. So let's use a formal Bayes rule to perform those calculations. So what we've just calculated, that 108 people will be tested as positive and only 8 of them will have cancer. So the ratio of people who have cancer among those who got tested positive is 7.4%. And so this is relatively, this is quite low. If you think about this, we started with accuracy. We have relatively good tests. Accuracy of the test is 80%, false positive rate is only 10%. But regardless of how good of a test it is, just the fact that the prevailing probability of having cancer is very low, so most of the people actually do not have cancer, leads to this very low probability of having cancer even after you got tested positive. So most women who test positive on a mammogram are healthy because the vast majority of women who receive mammograms in the first place are healthy. Now, if we try to use the formal way and we apply the Bayes rule to those calculations, so we want to calculate probability of cancer given the test was positive. I will write like this. We're just going to apply the Bayes rule, so it's a probability of test being positive given that the person has cancer times the probability of person has cancer divided by the total fraction of people who tested positive. Okay. While probability of being tested positive given you have cancer is 0.8. And the probability of having cancer to begin with is 0.01. And then the total number of people who got tested positive is probability of tested positive given that you do have cancer times the probability of having cancer plus probability of tested positive given you do not have cancer times the probability if you do not have cancer. So if you work out those calculations, you will get exactly this number, 7.4%.